Happy Monday morning, everybody. Today we're doing kinetic theory of gases, root mean square velocity, and the Maxwell distribution of speeds of molecules in a gas. I asked you in the instructions here to first go ahead and read chapter 13-10 and 11. Do it! If you haven't done it, do it! But right now I thought it might be the first paragraph, actually, because there's some important points there, and I know that there are times when you may happen to skip. I was hoping to have a guest speaker come in and do this reading today, but it didn't quite play out. So here it is, chapter 13:10. I'm going to read the first paragraph out loud. If you already read it, hey, listen again. Here it goes. Chapter 13:10. The analysis of matter in terms of atoms in continuous random motion is called, that's right, the kinetic theory. We now investigate the properties of a gas from the point of view of kinetic theory, which is based on the laws of classical mechanics. But to apply Newton's laws to each of the vast number of molecules in a gas, greater than times 10 to the 25th per meter cubed at STP, is far beyond the capability of any present computer. Instead, we take a statistical approach and determine averages of certain quantities. And these averages correspond to macroscopic variables. We will, of course, demand that our macroscopic description correspond to the macroscopic properties of gases. Otherwise, our theory would be of little value. Most importantly, we will arrive at an important relation between the average kinetic energy of the molecules in a gas and the absolute temperature. That was the part I wanted you to get. Statistical averages and the average kinetic energy of molecules is connected to the absolute temperature. Check. All right. So, since I'm sure you read the rest of the chapter, let me just go through some notes quick on what I saw, or what are the important points. First of all, there's 4 postulates, and these are something you are responsible for knowing and understanding. The book outlined them nicely. You probably already wrote them down. If you didn't, here you go. So the 4 postulates of kinetic theory. A postulate's a basic assumption upon which the rest of everything else rests upon. And if they're wrong, well, then the whole thing's wrong. So, number 1, there are a large number of molecules, capital N, with mass m, traveling at varying velocities in a gas. Number 2, the molecules are relatively far apart. That's what makes them a gas. Number 3, the molecules obey the laws of classical physics. That's a big one. We're talking about conservation of linear momentum and conservation of energy in collisions. This is the perfectly elastic collision that we talked about last year with bowling balls. This was the reason, was to be able to talk about kinetic theory of gases. Now, the book does a really nice job on page 252, which I encourage you to go back and look at, but the derivation, it's a bit much for what we need to worry about. It is. It's just the vector sum of the collisions of gas molecules on the container. But this is what it all boils down to. We're introducing a new letter, capital U. U stands for energy. So U would be the internal energy of a gas is going to be equal to the sum of the average kinetic energies. So actually, you know what? I kind of backed up one line here. I'm going to say right here, U is equal to the sum of the kinetic energy of all the different molecules in the gas. That's the point. Now, what that tells us is that the internal energy could be equal to 3/2 pressure times volume. And if I look at the units, check it out, it's obvious. Pressure is Newton per meter squared. Volume, meter cubed. Oh, you see it, don't you? Nice. You're going to end up with a Newton meter. And what's a Newton meter equal to? Oh, that was so sweet. You all said it together out loud. It's a joule. So yeah, pressure times volume is actually energy. To be precise, because of the way we talk about the collisions between the molecules, the internal energy of a gas is said to be 3/2 pressure times volume. Now, because PV is equal to nRT, I can substitute in and get the internal energy of a gas is 3/2 nRT. And next, I'm going to do another substitution. And this is one I don't think that you have seen before. And that is this. N, which is the number of moles, is equal to the number of molecules divided by Avogadro's number. Oh yeah, you already knew that. I think you knew that. What that's introducing is this capital N, which stands for number of molecules or atoms, depending on what the gas is. Now, what that allows us to do is to rewrite this formula for PV equals nRT. And now that I look at my notes again, I think I'm going to take just a moment and write that right down here. We'll get to the velocity in a second. So if PV is equal to nRT, jerk, but N is really N, if little n, is really the number of molecules divided by Avogadro's number times RT. You know what we have here? We have two constants, R, the ideal gas law constant, and Avogadro's number. And do you know what we can do when that happens? We can actually substitute in a new constant. And that new constant is lowercase k. That's a lowercase k. And it stands for Boltzmann's constant. I'll pick it up there on the next page of notes. Now, since the sum of the kinetic energy of all the molecules is equal to 3/2 nRT, I can take the sum of all the kinetic energies by multiplying by n. What happens is the n on both sides of the equation cross off. And what this is actually a measurement of is the average kinetic energy of all the molecules. That means when we take the square root of an average, it becomes the root mean square. All right. Now, I feel like those notes were not complete enough, so let's pick it up right here. Who's got a question? Yes, we still have more to do. Is that your question? All right, let's look. Next page. All right. In the past, we've talked about the ideal gas law. An ideal gas is one that follows the four postulates in the kinetic theory. You know what this ignores? Like things that intermolecular attraction and things like that in the gas. So an ideal gas is one that follows these four postulates. Okay, now I'm going to pick it up here. The internal energy of a gas, U, is equal to 3/2 PV. That means the internal energy of a gas would also be equal to 3/2 nRT. And as I just showed you, if we substitute in capital N divided by Avogadro's number, we end up with a new constant, R divided by Avogadro's number. If I take R, 8.31 joules per mole Kelvin, and divide by Avogadro's number, atoms or molecules in a mole, I end up with Boltzmann's constant, 1.38 times 10 to the minus 23rd joules per Kelvin. And that's known as Boltzmann's constant. What that means is if I rewrite my formula for the internal energy of a gas, it's going to be equal to 3/2 capital N KT. Now, you're probably thinking, what the? This is too many formulas all at once. Relax. It's all just a slightly different form of the same formula. That's it. That's all we're doing. You got this. Now, how does it come into play with root mean square velocity? Well, the entire idea of kinetic theory is that there are molecules in a gas moving around at varying speeds. And they collide with each other. They collide with the walls of the container. And as they do that, they obey classical physics. Momentum and kinetic energy have to be conserved in these collisions. right? Otherwise, if you just let a sample of gas sit there, over time, what would happen? If it lost energy, they'd all just slow down. But that's not what happens. So somehow there's a relationship between the temperature of the gas and the velocity. Let's see if we can pull that apart a little bit more. If we look at this form of Boltzmann's constant, the internal energy of a gas, this form of internal energy. The internal energy of a gas, U, is equal to 3/2 times the number of molecules times the constant times the temperature. You know what that means? That means that the internal energy of the gas is directly proportional to the temperature. Yeah, that's the key. And since the internal energy is related to the kinetic energy of the molecules, that means that the kinetic energy of the molecules is also directly proportional to the temperature. Yeah, that's the key. So now, root mean square velocity. If we take a look at it in terms of, I'm going to look on the left side of the equation here. I'll work my way through and then come over and do the right side. If we start with the internal energy of a gas is equal to 3/2 nRT. I multiply the sum of all the kinetic energies times n. If you're getting deja vu, it's because I already did this. Little n crosses off, and I get 1/2 m v squared equals 3/2 RT. Now I wrote a big M there because that's going to be the molar mass of the gas. Now, I solve it up for R. I solve it up for V. Take the square root. And when you take the square root of an average, if I could go back in time, I'd write an average over that. I end up with 3 kT over m. Now, this is the molar mass. Now, for oxygen, the molar mass is 32 grams, or 0.032 kilograms. It's how much a whole mole would have for mass. Okay, now, that is one way to calculate the root mean square velocity. There's another. And that is if I start with this new formula, utilizing Boltzmann's constant, 3/2 capital N kT. Now, the internal energy of the gas is just all the molecules times each individual molecule's average kinetic energy. Big N cancels out. The 2 underneath cancels out. Divided by the mass of one molecule or atom. And I end up with the root mean squared is 3 kT divided by little m. Now that little m would be the mass of one molecule in kilograms. So I got to be careful. And I'm going to talk about it again in just a second, but in an effort to foreshadow, oxygen gas, O2, is 32 atomic mass units. But since Boltzmann's constant has joules in it, that's got to be converted into kilograms. I'll explain how to do that in just a bit. Okay, so if I back up, here we go. Kinetic theory of gases you just read about. There's 4 postulates that you must know. There's a nice derivation in the book you might want to check out. But basically, the internal energy of a gas is related to 3/2 PV, 3/2 nRT, and 3/2 nKT, as I kind of showed here. Then came up with 2 formulas for the root mean square, and you can use either one of these when solving problems. Okay, so let's see how that looks, because there's a classic error that you can make either way, and what I've done is I've kind of shown what that error is so you can avoid it. I'm first going to show you the mistake. So if you're barely paying attention, this is the part that's wrong. Now, 3/2 kT divided by mass. Let's say we're talking about oxygen. What is the root mean square velocity of a sample of oxygen gas at 20 degrees Celsius. That's room temperature. Okay? Let's do it. So if I do 3 square root of 3 RT times mass, 3 times R times the temperature divided by 32. You know what I get? 15.7 meters per second. 15.7? I feel like I could catch that. That's not very, that's faster. That's slower than a fly. Molecules are moving much faster than that, I guess. So what was wrong? What's wrong is this mass has to be in kilograms per mole. And this is in grams per mole. So what do I have to do? If I convert the molar mass into kilograms, I get the velocity of oxygen at room temperature. The root mean square velocity is 478 meters per second. Now, different molecules of gas are going to be traveling at vastly different speeds. That's where the Maxwell distribution of speeds is going to come into play. So that 478 is the root mean square. You could kind of call it an average. Okay, but it's going to be a distribution of that surrounding that velocity. Okay, so root mean square. If we do 3 little n RT, this has got to be in kilograms. Now, if we utilize our other formula, 3 kT divided by m, this is wrong. Now, 3 kT divided by m. If I do 32 u's on the bottom, I get a velocity of 1.59 times 10 to the minus 20 meters per second. That is totally wrong. Totally wrong. Anyways, they're not even moving, right? So the conversion factor that I have to be aware of is 1 U is equal to 1.66 times 10 to the negative 27. That's the key. So watch when I do the math out. Root mean square is 3 kT divided by 32 U's times 1.66 times 10 to the minus 27 kilograms per U. And in fact, you know what? I'm going to take a moment and actually write this in with the units shown so that you can see exactly what I was doing. So 32 atomic mass units is the mass of 1 oxygen molecule. And then atomic mass units to kilograms, there's 1.66 times 10 to the negative 27. So that cancels out, leaves me kilograms, which works with Boltzmann's constant, which is in joules. And what do I get? I got it! 478 meters per second is the root mean square velocity. All right. That's that. If you're not feeling slightly overwhelmed, that's because you're just dazing out. What you may want to do is watch the video again, this time not in fast forward, and write down some of the formulas that you need to know on a separate sheet. I'm going to leave it to Ms. Wu to explain the Maxwell distribution of speeds. She's more smart than I am. Listen to Ms. Wu. Go back through these. Do your own problems if you need to. Take care of yourselves.